Welcome to our Chapter 7 problem solving video. In this video, we're going to go mainly over balancing chemical reactions. However, we're going to touch on all the various topics of Chapter 7. Just to remind us, Chapter 5 was balancing charge in a chemical formula. Chapter 7 is balancing chemical formula or chemical reactions, not chemical formulas, chemical reactions. Chapter 6 introduced mole calculations into chemical formulas. Chapter 8, we're going to introduce mole calculations into chemical reactions. So, focusing on chemical reactions today in this week. So, our first question, we're going to cover about 4 or 5 questions from the homework. Number 25 kind of just asks us, is this consistent with chemical reactions occurring? Why or why not? Solid copper deposits on a piece of aluminum foil, and a blue copper nitrate solution dissipates. So you have copper in solution ionized with nitrate. That's a very blue color. And then that color changes to clear and colorless, and you see copper metal depositing on the aluminum foil. This is a clear and classic sign of a redox reaction. You're transitioning aluminum metal into the solution. It's becoming aluminum nitrate, and the copper is getting reduced and becoming copper metal again. Liquid ethyl alcohol turns into a solid when placed into a low temperature freezer. So physical changes are never chemical reactions. A physical change is, there's a couple examples of physical change, but our most classic one is a phase change. So changing from liquid to solid or freezing is a physical change. So number C, we've seen this. A white precipitate forms when barium nitrate and sodium sulfate are mixed. We didn't see it with sodium sulfate and barium nitrate, but we saw this with calcium nitrate and sodium carbonate. Calcium carbonate precipitates out. That was our indication that a reaction happened. So C, definitely a reaction. We've seen this one. We can feel comfortable with this. A mixture of sugar and water bubbles when yeast are added. After several days, the sugar is gone. If something that was there originally disappears, that's essentially the definition of a chemical reaction. Chemicals have rearranged, or elements and atoms have rearranged their orientation to make new forms or new compounds. That's what yeast does, is it metabolizes or ingests sugars and excretes out ethyl alcohol, as well as a couple other things. But primarily people use yeast to either ferment things or create alcohol. So moving on to the next question, we have kind of a variation of the challenge question. So this is C6H12O6. This is, sugar, glucose. It's still an oxidation reaction. It's not a combustion reaction, but instead of taking a hydrocarbon fuel like octane, which we will be doing, we're going to take sugar, react it with oxygen, do the same type of reaction, and get off carbon dioxide and water. Now, the big difference between the cellular respiration reaction and the combustion reaction is that cellular respiration happens at room temperature, and water will remain liquid. Combustion happens at several hundred degrees Celsius, sometimes even several thousand degrees Celsius, and so you can't have liquid water at those temperatures, so we have gaseous water. In order to balance these chemical equations, we want to make sure that the same number of atoms are on each side of the periodic table, or on the reaction scheme. So we want the same number of carbons on the left and the right. We want the same number of hydrogens in the starting material and the products. Same thing with oxygens. So I recommend that you put these out on a chart, reactants over here, products over here, and kind of go back and forth balancing. But remember, we want to balance our pure elements last, so oxygen would get balanced last, and then we want to balance our least electronegative atom within a compound first. So hydrogen is our least electronegative atom out of any of these. It's not a pure element, so it's going to be the first thing we want to do. We have 12 hydrogens over here and 2 hydrogens over here. So putting a 6 in front is the quickest, easiest way to solve this. After hydrogen, we want to go to carbon. We have 6 carbons over here, 1 carbon over here, so we'll put the 6 in front. Now we have to deal with oxygen. We count up. We have 12 and 18. But we already have 6 over here. So we need to get 12 oxygens just from the O2. So we can put a 6 in front of there. 6 times 2 is 12. I recommend that you have your type of note-keeping devices, whatever method you use, whether it's a chart, whether it's, just scratches, however you choose to do it. Keep notes of what you have when you have it as you adjust them. So we've talked about, chemical reactions. We can also come up with different formulas or equations, so to speak. And so one of those is the ionic and net ionic. The complete ionic is where we take every one of these ionized species and put them into their separate ions. So in an aqueous solution, hydroiodic acid is not hydrogen iodide. They're not still bonded together. They're ionized and they're dissolved by water. Same with potassium hydroxide. However, water, it's designated as a liquid. It's not AQ. It's not ionized. Same thing down here, calcium sulfate. It's a solid. So that means it precipitated out of the reaction. It's not ionized. We wouldn't show these as separate ions. We'll get into this. So the complete ionic equation, we're just completely ionizing everything that's ionized. Hydrogen plus, iodine minus, potassium plus, hydroxide minus. Remember, we keep our polyatomics together because the polyatomic, although it has an ionic charge, the oxygen and hydrogen themselves in the OH are not ionic. It's the entire species that has an ionic charge to it. Slight difference. Those will convert into water, potassium iodide, which is potassium plus and iodide minus. We would call this a neutralization reaction because we have an acid and a base neutralizing each other to give us water and a salt. The net ionic equation is what happened, what displaced each other and is no longer ionized or is no longer soluble. In this reaction, hydrogen displaced potassium in a double displacement reaction, and water was the new thing that's not ionized. It's not a precipitate because it's in the same phase. A liquid and water are in the same phase. But it is a non-ionizable species, so we would keep it in its unionized form. Whereas the ones that came together, we would leave in their ionized form in the reactants or in the starting materials. In the products, they're not ionized, so we don't ionize them. Moving to the next one, kind of same idea. We want to ionize every single species. However, when we have sodium sulfate here, there's one molecule of sodium sulfate here, but there's 2 molecules of sodium in it, sodium ions, 2 atoms of sodium ions. So we want to put the 2 coefficient, leading coefficient, not the subscript. So you'll notice on our ionic equations or our complete and net ionic equations, the subscripts are only maintained by the polyatomics or by non-ionized compounds. For our ionized compounds, any subscripts that they had become leading coefficients rather than trailing subscripts. Again, polyatomics, we don't break them apart. So we have our net we have the net and then the total ionic equation. So moving on, kind of same thing. We have a little bit more of a fancy polyatomic here. I won't give you organic polyatomics just because it's not worth you trying to memorize, acetate polyatomics and, distinguishing acetate from formate from oxalate. That's not what this class is about. We're going to do Gen Chem. So here's just a problem from the back of the book. You can see it. So here's our polyatomic acetate. It's just a functional group. We have 2 hydrogens because we have 2 molecules of this acetic acid. Again, 2 sodiums because we have 2 sodiums up here. And we're just making sure that everything balances out. We want to make sure that the number of atoms I start with are still equal to the number of atoms I end with. We still have to do the balancing. But in this case, the equations were balanced for us. And we just have to ionize everything appropriately. making sure that things that have 2 minus charges should have 2 minus charges, and that they're balanced out against 2 positive 1 ions, or a single positive 2 ion. We don't have any +2 ions in here, so we only have the -2 carbonate. So we'll have to have 2 sodiums to account for. So these ionic and net ionic equations are fairly straightforward, and we're not going to focus on them much in this chapter. We're going to do, this example because it's part of the homework. It's good for you to get practice with a variety of different problems. But the main thing that we're concerned with is balancing chemical reactions, not these ionic reactions or the net ionic. They're similar. We'll use them in redox chemistry, which is chapter 16. But, we have another 8 chapters before we get there. So keep it in the back of your mind. But we just take our balanced chemical equation, and for the full ionic, we just completely separate all the ions. For the net ionic, we separate the ions that interact in some type of chemical reaction. So ammonia and hydroxide come together. Hydroxide pulls off one of the protons from ammonia to give you ammonia from ammonium. And hydroxide picks up that hydrogen and becomes water. These are the 2 non-ionized things. These are completely covalent compounds. These are completely ionized polyatomics, or polyatomic ions. So you want to be able to balance these. I'm not going to make you memorize what, gases are prone to being produced from polyatomics. We've mentioned that CO3 is going to be the only one that we deal with, but in the last example, we saw that ammonia can also be displaced as a gas. Ammonium can turn into ammonia. We'll see that SO3 is also prone to making SO2 gas, or sulfur dioxide. Or actually, I think it's disulfur oxide in this case, but we'll see in a second. And then hydrogen iodide gives off dihydrogen sulfide. So these aren't things you need to memorize, but we want to be able to balance these gas reactions. So luckily here, we have 2 protons, 2 protons, 1 sodium, 1 sodium, 1 bromide, 1 bromide. Since the carbonate breaks apart, we don't have a carbonate over here. We have to count each individual atom. We can't count the polyatomic. So carbon, there's 1 carbon, 1 carbon. 3 oxygens, 1 oxygen, 2 oxygens. Nice and easy. CO2 is our gas. I would expect you to know that CO2 is a gas. Most people have heard about CO2 as, greenhouse gas. At least by that logic, you should know that CO2 is a gas. All right, the next one, we mentioned we can displace ammonia as a gas. And so this is also a neutralization reaction, not just a gas evolution reaction, because we're taking 2 salts, an acid and a base, reacting them to get water and a salt. Now, it also happens that it blows off ammonia gas, but that's just another way that we could describe this. This is a neutralization. It's also a gas evolution reaction. So going to nitric acid and potassium sulfite. Sulfite salts are prone to giving off sulfur dioxide, and then the relating neutralization salt. Again, potassium sulfate is a base because it could be in the acidic form sulfurous acid, not sulfuric. Sulfuric acid relates to sulfate polyatomic ion. This is the sulfite polyatomic, so it's sulfurous is the acidic naming. We have the flowcharts from that in chapter 5, so you don't really have to remember that, but just something to keep in mind. We have an acid, nitric acid, reacts with a base to give us water, a salt, but it also kicks off a gas like in the previous reaction. So we could define both of these as acid-base / neutralization reactions or gas evolution reactions. Hydrogen iodide, or hydroiodic acid, mixed with lithium sulfide, gives us hydrogen or dihydrogen sulfide gas and lithium iodide. We would not call this a neutralization reaction because we didn't produce any water. Because we only produced gas and lithium iodide, this is just a gas evolution reaction, even though hydrogen iodide is an acid. Lithium sulfide we wouldn't really define as a base. So that's going to be all of the questions for today. We will cover the challenge question for Chapter 8, I mention it in Chapter 7 lecture, but we're going to do the combustion of octane. So you're going to need to know what the complete combustion of a fuel is. A complete combustion reaction gives off CO2 and water. And then you're going to need to balance, octane plus oxygen goes to CO2 and water. It's a pretty, involved balancing, but that's as hard as it's going to get for this class. So if you have any questions or want to see some more variations of the challenge question, make sure you reach out to me. Otherwise, I'll see you in lab this upcoming week.